Welcome everyone to OpenSSL and RSA for beginners. Here we're going to be understanding the math in the Wikipedia page, encrypting files with OpenSSL, and solving one PicoCTF challenge. Let's start by creating a private key. The private key contains P and Q, which are very large prime numbers, randomly generated. This means each private key is different. N equals P times Q, also known as the modulus. This has to be very large, so that it's difficult to factor into P and Q again. This is what RSA is based on, the difficulty of this, even for some supercomputers. Let's look at the help for this function. Here we see the default public exponent is 0x10001, a very common one. 3 is also fairly common. I'll leave it as the default. Also note that there is a minimum key length of 512. Any lower than this will result in a key size too small error. Let's output this to a private key. As you can see here. And now to extract the information contained in this base64 encoding, we can do OpenSSL, RSA, no out, input the key we just created, and /text to look at the values. We see prime1 and prime2, or P and Q. We see N, or the modulus, which is P times Q, the default public exponent, remember the hex value, and the private exponent. We can verify that the key length is 1024 bits. If we do /modulus, we get the modulus. If you don't have PyCryptodome installed, you can install it like this. I already have it. We can import long to bytes. And then if we look at the length of the modulus, just converting to hex with from x with 0x, we see it's 128 bytes, 8 bits in a byte, so 128 times 8 gives us 1024 bits, which is correct. Now let's look at how the private exponent is calculated. This is often denoted by the letter D. D equals the inverse of E mod lambda n, says Wikipedia. But read lambda n is the Carmichael-Toshan function, but in the original paper the Euler-Toshan function is used, which is phi of n, which is p take 1 times q take 1 used instead. OpenSSL also uses this instead. So that's phi equals p take 1 times q take 1. Let's just copy the values for p and q. I'll do it manually. And now I'll just clean this up a bit. Get rid of all the spaces. Colons. And new lines. and convert to base 10. There we go. We have P and Q. So we can calculate phi. And once we have phi, D is the inverse of E mod phi. We can use the Python power function for power. Where E is the default public exponent. And if we look at the hex of D, we can see this does indeed match our private exponent. 9E, 4C, 9E, 4C, etc. Once you have a private key, you can use this to generate a public key. To do this, we do OpenSSL, RSA, input our private key, output a public key, and write this to, I'll call it public.pem. This is what the public key looks like, and this only contains N and E, we can see. I forgot to tag, sorry. Just N and E. None of the private information. Now let's look at encrypting messages and decrypting them with OpenSSL. So I'll create a message. As so. We can encrypt it with OpenSSL, RSA util, encrypt, in key is for public.pem. It's a public key. We're encrypting message.text, and I'll output it as encoded. Sorry, message.encoded. As we can see, now it is encrypted. So we encrypted it with the public key. Now we decrypt it with the private key. Input the encoded message, and I'll output it as decoded.text. And it has successfully decoded it. Let's move on to the Pico CTF challenge. We're given some values. I've already downloaded the file. Let's copy and paste these. So this is the ciphertext. This is N, and this is E. This is why it's important to have very large values of N. When it's too small, it can be factorized. I'm just going to use this website for convenience. These two numbers are P and Q. Now we repeat the same process to calculate D, the private key. Phi equals P take 1 times Q take 1. In fact, I might show that you can also use the Carmichael torsion function. So let's import LCM. Carmichael, I'll just say car. LCM of P take 1 and Q take 1. Now we can do D equals the inverse of E mod the Carmichael function. And now the message is going to be c to the power of d mod n. Obviously this is in text, so we're going to use long to bytes again. And we can do .decode just to turn it into a string, not bytes with a little b here. And there we go. I hope this has helped you in gaining a better understanding of RSA and OpenSSL. Thank you for watching.